Eu gostaria de convidar o vice-reitor da UFMG, professor Marcos Borato Viana. É o seu lugar, ótimo. Você não tem necessidade especial?
Não, mas fiz questão para inaugurar.
Tá certo. Eu gostaria de convidar o professor José Najib Cotrinharbe, diretor executivo. Deixa a direita lá para ele. O professor Marco Aurélio Romano Silva, que fará a apresentação e a saudação ao visitante. Gostaria de convidar o nosso catedrático, professor Michael Brammer. Eu passo a palavra ao vice-reitor para a abertura dos trabalhos.
Bem, bom dia a todos. Eu declaro aberto a sessão da inauguração dessa cátedra da IEAT e passo a palavra ao Alfredo para as explicações iniciais.
Eu não sei se é muito formal, já vou dizer, então, a programação. Eu vou falar um pouquinho sobre o IEAT, o que é o IEAT. Logo em seguida, eu passo a palavra ao professor Najib, que vai falar sobre a cátedra. Seguindo, o professor Marco Aurélio fará a apresentação do convidado, professor catedrático, e, finalmente, o vice-reitor fará o encerramento e teremos, então, a palestra do professor Brammer. Esse é o nosso cronograma. Então, sobre o IEAT. Se em discurso podemos utilizar um título, então eu diria: o IEAT inicia o ciclo de cátedras. O IEAT é a sigla de um Instituto de Estudos Avançados Transdisciplinares que tem por âmbito a pesquisa, com inserção no ensino e na extensão, e, por missão, a promoção da transdisciplinaridade mediante a aproximação, a articulação e o transpassamento dos campos disciplinares e áreas do conhecimento tradicionais. Com esse objetivo, o IEAT foi criado em 1999 para atuar, ele próprio, de forma experimental, sem similares em outras instituições brasileiras. Atualmente, estamos em processo de formalização do IEAT na UFMG e a proposta já está pronta para ser analisada pelo CEP, pelo Conselho Universitário, em futuro próximo. Para alcançar êxito em suas realizações, o IEAT procura trabalhar a estruturação de metodologias transdisciplinares através da articulação de contribuições de diferentes áreas. Essas metodologias, associadas às ideias de unificação e abrangência, são aqui entendidas como a articulação das contribuições das metodologias disciplinares existentes, dando lugar a abordagens fortemente contextualizadas, abarcando artes, ciências e tecnologias e gerando características novas. Não se trata, portanto, de propor uma metodologia geral ou uma metametodologia, nem uma soma das metodologias disciplinares disponíveis. As abordagens multi- e interdisciplinares já estão incorporadas à rotina de pesquisa e ensino da UFMG e, nesse sentido, a transdisciplinaridade representa uma busca epistemológica pelo novo. Essa é uma demanda bastante generalizada e o IEAT representa, no âmbito da UFMG, um locus privilegiado de ideias e da utopia. As metodologias transdisciplinares se distinguirão das abordagens multi, pluri e interdisciplinares, na medida em que estas não compartilham metodologias ou se compartilham, como no caso da inter, topicamente, não há perspectiva de unificação e abrangência. É evidente que a procura por metodologias transdisciplinares pressupõe a existência de objetos compartilhados e já solidamente trabalhados nos campos disciplinares que, historicamente, geraram conquistas importantes em diferentes planos do conhecimento e podem ser vistos a exemplos da inter como condição para a transdisciplinaridade. Em consonância com sua natureza de instituto de pesquisa, o IEAT atua como órgão articulador, interdepartamentos, supra-unidades acadêmicas, marcando suas atividades pelas características de ineditismo, experimentalismo e transitoriedade. Para citar uns poucos exemplos de atividades envolvidas pelo IEAT, listamos projetos de pesquisas, já em andamento, atividades de ensino, hoje estamos iniciando um curso na temática cidades, eventos, encontros transdisciplinares, residências, geração de literatura e hoje estamos lançando esse ciclo das cátedras IEAT. O programa de cátedras tem por objetivo possibilitar a permanência na UFMG por curtos períodos de tempo de pesquisadores experientes que possuam sólida formação e carreira disciplinares e que possam estimular e induzir estudos nas interfaces das disciplinas. O objetivo é que sejam desenvolvidas atividades acadêmicas de ensino, pesquisa e extensão em estreita interação entre o catedrático e os grupos que estejam desenvolvendo pesquisas afins e com a comunidade universitária em geral, que levem ao desenvolvimento e à disseminação da transdisciplinaridade. São 3 as cátedras FUNDEP e IEAT, na área das humanidades, na área das ciências da vida e na área das ciências da natureza. No presente semestre, pela primeira vez, será implantada uma cátedra FUNDEP e IEAT. Ela estará ocorrendo na área de ciências da vida e terá como visitante o professor Michael John Brammer, a quem agradecemos por haver aceitado o convite e agora deixamos a cargo do professor Marco Aurélio do ICB fazer a apresentação do catedrático. Para encerrar, gostaria de também informar que para janeiro próximo estaremos implantando uma segunda cátedra, nesse caso com o patrocínio da Fundação Forte, com a vinda do professor James Lynch. Essa cátedra terá como tema a questão transdisciplinar da criminalidade, violência e políticas públicas. Muito obrigado. Passo a palavra ao diretor executivo da FUNDEP, professor José Najib Coutrinhada.
Bom dia a todos. É uma honra para mim estar presente aqui no lançamento da cátedra FUNDEP e IEAT e dar as boas-vindas ao professor Michael Brammer, que inaugura essa cátedra. Em atenção ao nosso catedrático, eu vou falar um minuto sobre a FUNDEP e sobre a origem dessa cátedra. A FUNDEP é uma fundação de apoio às atividades da universidade, foi criada pelo Conselho Universitário da Universidade em 1974, vai fazer 30 anos no ano que vem. Basicamente, ela gerencia projetos de ensino, pesquisa, extensão, consultoria, prestação de serviços que a universidade faz através de diversos projetos. Então, a principal missão da FUNDEP é apoiar a universidade, então, nas suas atividades fins. Com o tempo, a FUNDEP atingiu uma estabilidade financeira muito boa, e, então, o Conselho Curador, que é formado por professores da universidade, indicados pelo Conselho Universitário, passou a determinar que os eventuais resultados positivos que a FUNDEP tivesse fossem redirecionados para a universidade. Então, em 1986, foi criado o Fundo de Apoio à Pesquisa pelo Conselho Curador, que destinava, então, recursos para a universidade, que o Conselho de Ensino, Pesquisa e Extensão decidiriam em qual projeto aplicar. Em 1996, o Conselho Curador resolveu transformar esse fundo num fundo de apoio acadêmico, não só para atividades de pesquisa, mas também para outras atividades acadêmicas, mantendo a decisão de destino dos recursos a cargo do Conselho de Ensino, Pesquisa e Extensão da universidade. No ano de 2000, o Conselho da FUNDEP, na época presidido pelo professor Rênio Cardilho Vieira, do Instituto de Ciências Biológicas, decidiu criar outro fundo de apoio à universidade, chamado Fundo de Apoio ao Desenvolvimento Institucional da universidade, que começou, então, a ser repassado à universidade em 2000 e que, nos primeiros 8 anos, está destinado a financiar as obras de instalação de prédios aqui no campus da universidade, as obras do projeto Campus 2000. No mesmo ano, em 2000, apoiando a iniciativa que estava sendo iniciada pelo reitorado anterior, sob a direção do pró-reitor de pesquisa de então, professor Paulo Sérgio Beirão, também no Instituto de Ciências Biológicas, o Conselho Curador da FUNDEP resolveu fazer um tipo de doação para o IEAT, tá? Uma doação do tipo, que em inglês a gente chama de endowment, né? Para financiar e criar essa cátedra FUNDEP. A doação foi de R$1 milhão, tá? Disponibilizados ao longo de 4 anos, o recurso já está disponibilizado, e, basicamente, ele funciona da seguinte maneira: o principal, o R$1 milhão, não deve ser tocado, pelo contrário, o poder aquisitivo dele deve ser preservado, tá? E os rendimentos financeiros das aplicações desse fundo que serão usados para financiar, ao longo do tempo, a cátedra. Então, a questão de você tem lá um dinheiro semente de R$1 milhão, que tem que manter o valor aquisitivo de R$1 milhão, a ideia é essa, tá? E usa os rendimentos para financiar a cátedra, de modo que sempre você tenha condições de estar permanentemente financiando a cátedra, tá? A cátedra teve que esperar um pouco para ser implantada, não só pelo processo acadêmico de maturação do IEAT, a demanda desse tempo, como também pelo processo de criação do fundo, tá? Ele não pode ser sacado ou usado imediatamente após a criação dele, porque senão ele não teria tempo de maturar e de render. Então, chegou o momento, uma grande honra, nesse momento, estar dirigindo a FUNDEP e poder estar, nesse momento, implantando a cátedra. E também é uma oportunidade para a gente refletir sobre essas formas de financiamento alternativas para esse tipo de atividade, expansão nessa área, usar esse tipo de financiamento, que é sobre a forma desses fundos que geram rendas para financiar as atividades, que é uma forma de financiamento de atividades acadêmicas muito pouco usada no Brasil, tá? Ao contrário de outros países do mundo que têm, em algumas universidades, a principal fonte de financiamento de áreas de pesquisa da universidade, bancadas por esse tipo de financiamento chamado endowment, tá? Então, era isso que eu queria falar, dar as boas-vindas ao professor Michael Brammer mais uma vez, e eu acho que a estrela do dia é ele, nós não temos muito tempo que ocupá-lo. Muito obrigado.
Então, eu acho, em nome da universidade, do IEAT, a gente agradece a FUNDEP, na pessoa do professor Najib. Eu passo a palavra ao vice-reitor, professor Marcos Borato Viana.
Nós vamos fazer uma pequena inversão, porque aí nós já vamos direto para o Marco Aurélio para poder apresentar, e vamos ouvir, então, vou seguir a orientação do Najib, falar também rapidamente, em primeiro lugar, da importância que tem para nós na universidade o IEAT. É uma flor que tem que ser cuidada realmente com muito carinho, uma vez que, agora sim, né, ele desenvolveu-se, já fez várias atividades, mas agora está realmente desabrochando no sentido, primeiro, das suas cátedras e agora do primeiro curso temático sobre cidades, que vai ser também inaugurado hoje, que é uma coisa importantíssima. Eu acho que essa questão do IEAT, ela emblematiza de uma forma evidente uma coisa que a universidade vem fazendo durante há muito tempo e que nós, desse reitorado, temos enfatizado muito, que é a união da excelência com a relevância. É uma coisa fundamental para nós que essas duas coisas ocorram ao mesmo tempo, e o IEAT, o funcionamento do IEAT, emblematiza essa unidade entre a qualidade, entre a excelência e a relevância. Eu acho que esse tema que será tratado hoje, bem como o próximo, da próxima cátedra, que é a questão da violência, emblematiza a necessidade de se unir o máximo de rigor científico, o máximo de rigor metodológico, ao mesmo tempo em que que são abordadas questões altamente relevantes para a sociedade brasileira. E, por mera coincidência, eu poderia dizer que foi proposital, mas não foi. Na verdade, foi coincidência. Hoje também nós estamos abrindo, não sei se o Dr. Michael Brammer sabe, nós estamos sediando parcialmente, mas as principais atividades, sob o ponto de vista de reuniões, etc., inclusive de áreas transdisciplinares, estão ocorrendo aqui na abertura do Fórum Social Brasileiro. Está se dando hoje aqui em Belo Horizonte e aqui no UFMG, em particular, nós teremos atividades na sexta, sábado e domingo. Então, é o Fórum Social Brasileiro que exatamente tem essa abordagem transdisciplinar. Vão ser debatidos assuntos debatidos e comemorados e passeatas, etc. e tal, porque hoje, inclusive, inaugura com uma grande caminhada no centro de Belo Horizonte, do Fórum Social Brasileiro, que é a preparação do Brasil para o Fórum Social Mundial, que se realizará na Índia no ano que vem. Então, realmente, esse aspecto que nós estamos enfatizando, da necessidade que nós temos de unir a excelência com a relevância, quer dizer, ambas são faces da mesma moeda, não adianta ter alta qualidade sem relevância e também querer ser relevante sem que essa marca da qualidade que a UFMG tem, ela esteja também presente. Então, isso é um motivo realmente de muita satisfação, e nós agradecemos muito ao Dr. Brammer, que veio aqui colaborar, fala português, mas falará a sua aula em inglês, exatamente, né, na medida em que publica numa língua, pensa numa determinada língua, fica difícil em português. Mas ele também é um exemplo de transdisciplinaridade, na medida em que eu fiquei sabendo aqui que ele aprendeu inglês lendo as traduções de Agatha Christie e depois evoluiu para as grandes obras da literatura brasileira, Graciliano Ramos, e agora ele vai começar com Guimarães Rosa. Então, realmente, eu acho que é dessa forma que nós construímos um pensamento mais amplo, um pensamento realmente que nós estamos chamando de transdisciplinar. Eu acho que é na própria prática, né, na prática de vida, é que a gente consegue realmente avançar. Então, é com muito prazer que nós recebemos o Dr. Brammer. Queremos também enfatizar e agradecer a nossa FUNDEP, realmente o trabalho que a FUNDEP vem realizando ao longo dos anos, essa estabilidade financeira a que o Najib se referiu é importantíssimo, foi graças a ela que atualmente, eu não sei, ele não falou em termos de porcentagens, mas eu vou dizer aqui para vocês, do resultado operacional da FUNDEP, atualmente, anualmente, do resultado da FUNDEP são destinados 30% para o Fundo de Apoio Acadêmico, o Fundo FUNDEP, né, cuja distribuição é decidida pelo Conselho Universitário, e esse ano montou R$ 1.650.000, e 40% do resultado operacional, quer dizer, 30 mais 40, portanto, 40% desse resultado operacional são destinados ao Fundo de Desenvolvimento Institucional. Então, vocês estão vendo que do resultado operacional global, já 70% é uma forma de redistribuição para a universidade. Volta de novo para a universidade, não para aqueles projetos que geraram, mas para o coletivo. Eu acho que essa é uma forma importante de atuação da FUNDEP. Isso o que é anualmente, fora exatamente a cátedra, a que o Najib já se referiu, e fora todos os outros patrocínios que a FUNDEP também proporciona de forma mais pontual, mas que chega no final, sem comprometer o funcionamento da FUNDEP, quase que a totalidade do seu resultado operacional volta de novo para a universidade. Então, nós agradecemos muito à FUNDEP, na presença, na pessoa do Najib, mas, na verdade, agradecendo a todos os que antecederam, todos que dirigiram a FUNDEP, que tiveram essas ideias no sentido de a FUNDEP realmente se transformar dentro do Brasil na fundação que maior apoio proporciona à instituição, que, na verdade, é o motivo da sua existência. Então, agradecemos muito à FUNDEP, agradecemos ao professor Alfredo, a direção, ao professor Ivan, que antecedeu o professor Alfredo na direção do IEAT, e a todo o seu conselho científico, nesse esforço que vem sendo feito no sentido de fazer com que o IEAT realmente seja o protótipo dessa união entre a qualidade, a excelência e a relevância. Eu agradeço a presença de todos e eu vou passar então para o Marco Aurélio, para que nós vamos nos dirigir agora ao plenário e passamos a palavra ao Marco Aurélio para que ele apresente o professor Brammer.
Ok, obrigado. Bom dia a todos e boas-vindas a essa sessão de inauguração da cátedra. Coube a mim, então, apresentar o professor Michael Brammer, e eu fico muito à vontade para fazer isso. Eu trabalhei com ele muitos anos, mas então, apresentar o professor Michael John Brammer é, para mim, uma grande honra. Sempre que se tem a oportunidade, em uma mesma ocasião, essa que a gente está participando aqui hoje, de acolher, elogiar e homenagear uma pessoa que teve um papel fundamental na nossa carreira científica. O meu primeiro contato com o professor Brammer, que era então senior lecturer no Instituto de Psiquiatria, ocorreu em 1989, por intermédio da professora Ângela Ribeiro, do Departamento de Bioquímica do ICB. Eu fui aceito por ele para um curto estágio em seu laboratório, no Departamento de Bioquímica do Instituto de Psiquiatria da Universidade de Londres. Foi um estágio de iniciação científica na época, pois eu me encontrava no 9º período do curso de medicina, aqui na UFMG, sendo que 3 anos mais tarde, em maio de 92, o professor Brammer fez a sua primeira viagem ao Brasil, de várias, já está na 13ª ou 14ª agora. E naquele mesmo ano, em outubro, eu fui para Londres, com uma bolsa de doutorado sanduíche do CNPq, para trabalhar num projeto de tese, orientado pelo professor Marcos Vinícius Gomes e coorientado pelo professor Brammer. O período de 18 meses que eu permaneci lá foi extremamente produtivo e resultou em várias publicações conjuntas que deram origem a linhas de pesquisas que estão hoje consolidadas no nosso laboratório aqui, na UFMG, além de ter sido o início de uma colaboração que permanece e que tem se intensificado a cada ano, financiada por agências tanto nacionais quanto internacionais, como o CNPq e o Wellcome Trust. Naquele período, entre 92 e 94, o professor Brammer começava também, junto com seu então aluno de doutorado, Dr. Edward Bulmore, que hoje é Professor of Psychiatry em Cambridge, um projeto de análise de dados eletroencefalográficos usando fractais. Aquele seria, então, o início da trilha que levaria o bioquímico, formado em Leeds em 1970, a se tornar o diretor da Brain Image Analysis Unit em 1996 e ter a sua personal chair, a sua própria cadeira de Professor of Neuroimaging em 2000, contando com quase 200 trabalhos em periódicos internacionais de prestígio, tais como Science, Nature, PNAS, entre outros. Uma carreira que ultrapassou os limites da bioquímica, através da neurociência, tornando-se interdisciplinar. E que hoje, com a inauguração da cátedra IEAT FUNDEP Ciências da Vida, caminha para a transdisciplinaridade. O potencial de colaborações e interações na UFMG é enorme e nós devemos explorar ao máximo. Já nessa visita, foi plantada a semente de um projeto para o estabelecimento de um centro de ressonância magnética funcional e de análise de imagens, que deverá envolver pesquisadores das áreas de biologia, medicina, computação, física e engenharia. Nas palavras do professor Brammer, O ambiente de trabalho que ele vivenciou nas últimas 4 semanas, em termos de exposição e contatos com pesquisadores e alunos de diferentes áreas, e desenvolvimento de novas ideias, seria quase impossível no seu dia a dia em Londres, atingindo, a meu ver, um dos grandes objetivos da cátedra, que é o de ser uma fonte de indução de mão dupla. Eu gostaria, então, de terminar agradecendo ao IEAT e à FUNDEP pela iniciativa de criação das cátedras, a todos que trabalharam para a sua viabilização e ao professor Brammer pela sua disposição, motivação e envolvimento nesse projeto experimental que é de todos nós aqui da universidade. Obrigado, Mick. Seja bem-vindo.
IEAT, FUNDEP, Marco Aurelio, and virtually all the other people who have had any involvement in setting up this cátedra. It's a great pleasure for me to come and continue my work. As Marco said in his introduction, I've been working with people here in UFMG for about 13 years. And it's good to be able to continue that and to attempt to make an impact in the area of transdisciplinarity. This word doesn't exist in English, I should say, so more about that later. Okay, the main purposes of my talk, I think, are twofold. I'd like to start off by really introducing you to my history in science and the way in which I became involved in transdisciplinarity, and then to talk about some ideas that I've got here to extend my collaborations beyond sciences and into other areas that may be interesting. Okay, is that two? That's better. Okay, is that fine? Okay. I think we now live in an age where we're completely surrounded by images. We can't escape from images. Images are used to communicate in virtually every aspect of our lives. And this is not a new phenomenon. I'm currently buying a house in Spain, in Cantabria, in the north of Spain. And very close to my house are the Altamira caves, Paleolithic caves in the north of Spain. And here is an illustration from the ceiling of the La Cueva de Altamira in Cantabria. And this illustrates that many tens of thousands of years ago, people were taking enormous risks to get into the depths of these caves. These paintings are often in very inaccessible places. And notwithstanding the difficulty, people clearly saw that there was importance in using these images as a means of communication. And these images are of very high quality. You can see here, this is a drawing of a bison, a European bison, of extremely high artistic quality. So these images are of high quality. They may have had some religious significance. We still argue about their significance, but clearly presentation of images was very important to these people. So our love of images and our use of images in communication has not changed in many tens of thousands of years. What has changed is our ability to obtain images and to store them in digital form. And now we can do almost anything that we wish to do with images. We're only limited by our creative talent, our ability to write computer programs, our ability to manipulate images. And I think it's probably no coincidence that my change in career from biochemistry into brain imaging was motivated primarily by the fact that I love playing with images. I love writing computer programs to manipulate images. So apart from any scientific involvement, there is a very large creative impulse for me to get into neuroimaging. This is a little bit of my history. I started my career, as Marco said, in biochemistry in 1970. I graduated in biochemistry. My training was actually quite interesting. I trained in biochemistry, physiology, chemistry, and Oriental philosophy, Oriental religion. And I think the Oriental religion still stays with me in many of my attitudes to life. I got a PhD in biochemistry in 1974 and became a lecturer in neurochemistry at the Institute of Psychiatry in 1976. And most of my research... Okay, when I get too close, it feeds back. That's the problem. I continued my research in neurochemistry and neuropharmacology for 15 years, but I became increasingly interested in computer programming and in numerical methods in biochemistry. And then in 1991, I had two, I think, of the major influences in my career. I had the best two PhD students I've ever had working in my laboratory at the same time. I had Marco Aurelio, who's a good friend and longtime collaborator, and Ed Bullmore, who, as Marco said, is now the professor of psychiatry at the University of Cambridge. With Marco in the morning, I was doing biochemistry on the effects of scorpion and spider toxins on channels, ion channels in membranes. With Ed Bullmore in the afternoon, I was doing work on the fractal analysis of EEG and brain signal. This was a very interesting stage in my career. I start by talking a little bit now about these various interests of mine at that time. In the 1980s and 1990s, many scientists became interested in fractal properties of natural objects. And in a scientific sense, fractals are often used to measure the complexity of an object. Fractal is a term coined by the American mathematician Mandelbrot, who works for the IBM. I think he still works for IBM. And it comes from a Latin word meaning broken. And it's used to describe structures which show a property called scale invariance. And scale invariance means that as you magnify them more and more and more, the structure essentially looks the same. So basically the structure is essentially built up by repeating itself on larger and larger and larger scales. This is a very famous picture. This is the famous Mandelbrot set, which was in many student bedrooms in the 1980s. And in fact, my first creative impulse in imaging, I think, was to generate these images using my computer, which at that time was extremely slow. So these images took a long time to generate. And this is, in fact, in mathematical terms, this is a very simple object. It's just simply a series of solutions to a complex quadratic equation. That's all it is, but it generates this beautiful object. And here's a little bit about what fractal objects actually are. And this idea that they're built up by repetition of the same simple set of rules. So if we start at the bottom of this tree here, we can see that it simply goes and then branches. If we then take the next level and go next step, go and branch again, and then go and branch again, we gradually build up this object. A tree, this particular type of tree, is a perfectly fractal object, because if we look at it here, in its tip, it's exactly the same structure as down here. The reason why we became interested in fractals, myself and Edward Bullmore, was not simply because we like making pretty pictures, although we did like making pretty pictures. It's because we were actually interested in estimating the complexity of EEG, electroencephalography signals. We had an idea that maybe we could use the fractal dimension of an EEG, a measure of its complexity, to automatically detect seizures in people who had epilepsy. This was very important because these people were being monitored continuously. But normally, in order to check on events, a person would have to look at hundreds of meters of paper and extract from that paper the signals of interest. The idea that Ed and I had was to make that process much easier by presenting the results as an image, which was very easily intelligible. So this, if you like, was my first excursion into transdisciplinarity. This is my attempt to represent a complicated object in a very simple way, in the form of an image. And this was our first paper on EEG representation in fractal terms, which appeared in the Lancet Medical Journal in 1992, and was the start of a very long collaboration with Ed Bullmore, which still continues today. Ed has now moved to Cambridge, but we've just managed to get a grant from the National Institute of Health in the United States to continue our researches together. The interesting point, I think, is the next stage, which is how did I manage to get from EEG to brain images, magnetic resonance images. And this was a very interesting story. Ed's PhD thesis, and Marco may well remember this story, Ed's PhD thesis was actually called the fractal analysis of EEG signals. But Ed had a very bad problem in the middle of his PhD. He ran out of data. Absolutely no way that he could get any more data. So we had to start thinking of other ways to get him a PhD. And one way that we proceeded was that we made contact with a neurologist, the Institute of Neurology in London, who was interested in analyzing brain scans. And she was interested in a very simple question. Did the boundary between the gray matter in brain and the white matter in brain, gray matter being the area that contains neurons, the transmitting nerve cells, the white matter being the area that contains the nerve fibers, did the boundary between these two areas change in mental illness, like schizophrenia, in which there was possibly a developmental component? This is a quick image of a brain, just to show you what this boundary looks like. Over here, we've got gray matter, usually on the surface of the brain, but not always so. Highly convoluted, highly folded. And here, in the middle of the brain, we have white matter, which is the area which contains the fibers which allow the neurons to communicate with each other across large distances in the brain. And our first attempt to use fractal analysis on this boundary, on the boundary between gray and white matter, showed some interesting results in patients with manic depression. We actually saw quite interesting changes there, and in schizophrenia. One of the most interesting findings to come out of that was that the fractal dimension of that boundary was highly correlated with the IQ of the individuals who took part in the study. So we thought we maybe had an automated method of measuring intelligence without asking people questions, but we've never actually pursued that. However, and this again is another story of how things tend to happen largely by accident and partly by scientific design. Extracting the boundary between the gray and white matter turns out to be a very time-consuming process to do it manually. So the next thing that Ed and I decided to do was to see if we could extract it automatically. And this involves a process called segmentation. Segmentation is separating two objects in an image so that you can deal with them separately. You can analyze them separately, you can measure them separately. And we were interested in separating the gray matter from the white matter of brain automatically. And we published a paper on this in the journal Neuroimage in 1995, I beg your pardon. The first, I think, very reasonable method of automated segmentation that would extract this boundary with high reliability. And this brings me, I think, to the most formative year in my career, which was 1994. At this time, I was still trying to do biochemistry as well as neuroimaging, but this proved to be almost impossible. I had to make a choice. I had to either be a biochemist or a neuroimager. I don't think I could manage to be both. And I discussed this with Marco. I remember telling him about this. I said, it's very difficult to continue being biochemist and a neuroimager. And I decided, maybe rightly, maybe wrongly, to become a neuroimager, which is what I am today. And at that time, the Institute of Psychiatry obtained, which is where I work in London, as Marco said, obtained the first functional magnetic resonance scanner outside the USA in the world. We were the first people outside the USA to be able to do functional brain imaging. Functional brain imaging is a technique in which you can actually see which parts of the brain are involved in performing specific experiments in the scanner. I'm sure you've all seen pictures of functional magnetic resonance imaging results in magazines and on television where a certain part of the brain is activated when people see someone they like or when they see someone they don't like or that sort of thing. It's very common now to see these images. And this is just a brief history of this technique, because I'm sure most of you in this audience are not familiar with functional imaging. And functional imaging is basically what I do to make a living, so in London at least. The magnetic properties of oxygen-carrying pigments in the blood have been known for a very long time. In the 1930s, the American chemist and Nobel Prize winner Linus Pauling first discovered that these chemical compounds in the blood, hemoglobin, deoxyhemoglobin, had magnetic properties that were different from each other. And at the time, this was just an interesting observation. It really didn't mean very much to anybody. Slightly later, people began to really do a lot more work on this, and by the 1980s, there were the first demonstrations that the changes in images that you could detect by studying the magnetic difference between oxyhemoglobin, which is the form which is bound to oxygen, and deoxyhemoglobin, which is the form that is not bound. By studying the difference between those two in a brain scanner, it was possible to detect differences that were large enough to make into images. And this was the foundation of what we now call functional magnetic resonance imaging. And the first functional magnetic resonance imaging experiment was published in 1990 by an American radiologist physicist called Ogawa, using something called the bold contrast method, which is blood oxygen level dependent contrast. And this was the time when we started functional imaging in the Institute of Psychiatry. In 1994, when I began this topic, there were possibly 4 groups in the world, 5 groups in the world doing this subject, and maybe 4 papers a year appearing in the journals. Now there are possibly 4,000 groups in the world doing this topic, and 10,000 papers a year appearing in the journals. I don't know how many. This is the basis of this technique, and this, I thought it was probably very silly to talk about functional imaging and not give you an approximate idea of how it works. If any of you in this room has a thought, and I hope at least during some part of this lecture some of you will have some thoughts, if any of you has a thought, the part of your brain that you're using for that process, or if you see an object, the part of your brain that you're using for that process will increase its activity. The neurons, the cells in the brain that send messages to each other, will become more active. This is an energy-requiring process. In order to continue being active, these cells then require a supply of energy from the blood. So several things happen, and they're shown on this slide. In the top left, you can see that there's an increase in the blood flow into the area at the back of the brain. In this case, the back is on the right, front is on the left. An area called the occipital cortex, which is the area we use to deal with images. Another thing that happens at the same time is there's an increase in the amount of glucose supplied to that part of the brain. And that you can see in the second slide along in that row. There's also an increase in the amount of oxygen use, but it's very small and it can barely be seen. It's almost invisible on the third slide along. The fourth slide shows something quite interesting, that because the blood supply is increasing, there's more oxygen around that area that's active than there was before this person doing the experiment was looking at images. But the oxygen isn't at that point being taken up into cells. And what happens is that this residual amount of oxygen in the occipital cortex is causing the magnetic resonance imaging signal to change enough for us to pick it up. There's a change in the signal of about 2 or 3%. We now know that this signal is happening in the area called the dendritic tree, which is this area around here. We didn't know that until a couple of years ago. This is due to the work of a scientist called Nikos Logothitis. So we now know a lot about this phenomenon. But principally, this is a method that we can use to put people in a scanner, to have them perform a task, and to non-invasively, without causing them any harm, to find out a great deal about brain function. And I think it's pretty obvious to anybody who's interested in physiology and neuroscience why this technique is so valuable. And it's already made an enormous contribution to psychiatry, psychology, neurology. And I think will continue to do so. So this is a series of fMRI images which I've computer enhanced just to make the brightness change a bit bigger. And this is a person listening to a word. At the top left here, nothing is happening. And then we expose this person to a single word, and what happens is there's an increase in brightness here in the temporal lobes. These are the areas either side of the brain. And this is the area that deals with processing sound in the brain. And then as the effect dies away, the image intensity goes back and returns to normal. It takes about 5 seconds for your brain to produce a response to increase the glucose, the oxygen level, after you've started thinking. So the one problem with functional imaging is it doesn't image electrical events in the brain in real time. It takes about 5 seconds to produce a response. This is not a serious problem for many of the studies we do, but we are working on ways of improving it. Now, I've talked about the science, but, just to tell you what functional magnetic resonance imaging is, because it's pretty stupid for me to actually give a talk about most of my career without explaining what the scientific basis to that career is. But in fact, the problems in fMRI are part of the reason why I was interested in coming here to take up this cátedra. Because one of the major problems is how on earth do we communicate the amount of data that we acquire in an fMRI experiment in a form that's accessible to clinicians, to members of the public, to people who will want to understand the results. How do we do this? Many of you in this room will use computers in your everyday lives. Probably all of you use computers in your everyday lives. One 5-minute experiment in a brain scanner will generate 25 megabytes to 50 megabytes of data. In one day, I generate 1 or 2 gigabytes of data. And I have to process that data. And my job in the Institute of Psychiatry in London is to get that data into a form such that it can appear in scientific journals and that people can understand it and that we can communicate it to scientists and to non-scientists. So one of my great interests in life, possibly my greatest interest in life, is how do we represent data in a form that is not only accessible, but is fun to take on board. Okay, here's just an illustration of an fMRI experiment to show you how it works. This is an experiment where we're actually performing 2 tasks in the scanner at the same time. The person in the scanner is listening to words, and the words are being repeated. It's about every 39 seconds. We have a period without words and a period with words, period without words, period with words. And then at the bottom, we have images. We're presenting no images, and then images, no images. And these 2 things are running at the same time. And it's interesting that if we present these at the right frequencies, it's perfectly easy for us to analyze these 2 sets of events at the same time. And here's a short movie of an fMRI experiment where we can see the visual response, which is down here at the bottom of the brain, and the auditory response, which is up here, happening at different frequencies. So all I've done to make this movie is I've analyzed the experiment, and then I've simply made the results into a movie loop. So I can actually show these activations. And in fact, this is quite a useful way of presenting fMRI data, because essentially fMRI, functional MRI, has the same relationship to the standard structural MRI, which we're all familiar with in hospitals, that a movie has to a still photograph. In a structural imaging scan, if you go to a hospital, if you're unfortunate enough to be involved in an accident, and you go to a hospital and you have an MR scan, what they will be doing is looking at the structure of your brain. They will be seeing if there's any change in the structure of your brain. If you imagine the process of getting that scan being repeated every 3 seconds or every 2 seconds during a 5-minute experiment, you have functional MRI. So if you think of it like this, a structural image is a still photograph, a functional image is a series of pictures made into a film, if you like. And my job is to interpret that film, to analyze that film, and to communicate the results of that film. Now, we're very used to 3-dimensional representations in fMRI. The brain is a 3-dimensional object. Functional imaging data is in fact 4-dimensional. 3-dimensional brain at lots of time points. So it's a 4D, 4-dimensional object. Here we can see an auditory response represented in quite a lot of different ways. We can see it on the surface of the brain over here in the top left, and then we can see various cutaway images where we try to show where this activation is located in relationship to the structures of the brain that surround it. And this is very useful for example, neurosurgeons who might wish to perform an operation on a patient and might wish to have a lot of clear information about exactly where an activation is located. But again, this is a question of presentation. This is a question of transdisciplinarity. This is a question of getting over your ideas to people who are not experts in statistics and image analysis, and actually making the process of understanding the data intuitive, making it simple, making it accessible. Now, I'm not going to talk for very long about the actual process of data analysis because it is enormously complex, and most of the papers are highly technical and involve areas of statistics that I'm sure are of very little interest to most of the people in this room. people who are interested know me well enough to ask me about these processes, and I'm perfectly happy to describe them. But the major problem we have in fMRI data analysis essentially is the signal change is small. The brightness of the image only changes by a few % during these experiments. And there are all sorts of things happening in the scanner that can mask this process. For example, if you move in the scanner, it will create problems. If you breathe in the scanner, it will create problems. So virtually everything you can do in a scanner as well as the experiment will create problems. And one of my major occupations over the last 5 years as a statistician, which I guess is what I'm now primarily, is to attempt to extract information from these signals in a reliable form so that those maps that we make show accurately where the brain is activated and don't just show parts of the brain where a person happens to be moving around in the scanner. And we published the first major paper we had published in this area was in 1996, again with Ed Bullmore. And we've then gone on right up to this day. And in fact, interestingly enough, our latest methods of analysis use fractal methodology. We've now discovered that a lot of the noise that we have to deal with in fMRI data sets is in fact fractal. So by using fractal analysis methods, we can get over that problem. Okay, as Marco said, we published enormously in fMRI over the last 10 years. And if I attempted to give you even a quick snapshot of the kind of work we've done, it would take me 3 hours at least. We published in psychiatry, we published in neurology, we published in psychology. We published on virtually every psychiatric disorder imaginable: schizophrenia, depression, anorexia, attention deficit, obsessive compulsive disorders. You name it, we probably tried to study it in the scanner. But interestingly enough, along this period, we've also been interested in looking at some natural phenomena that occur in normal people in the brain, or certainly people who are not ill, because we have an interest not just in looking at how the brain functions when you are unwell, we've got an interest in how the brain functions when you're perfectly well, its normal function. And one of the first things, a couple of short presentations that I want to make to you. The first is on synesthesia. Synesthesia is a very interesting phenomenon because synesthesia is a condition where someone will, for example, hear a word, for example, the word 4, the number 4, and they will see a color. To these people, the number 4 is colored. 4 may be purple, it may be green, it may be red, it may be yellow. And there's a lot of interest in exactly what's happening in synesthesia. And beginning of 2002, we published a paper in Nature Neuroscience showing that what happens in synesthesia is very interesting. These people have abnormal wiring of the brain, and they have a fairly direct connection between the auditory cortex and a part of the visual cortex that's involved in processing color, called V4, which is this area down here in red. So, well, the interesting thing about synesthetics is they have abnormal wiring and they have cross-sensory processing that most of us simply don't have. For them, sounds are colored. And one of my abiding interests because I'm actually interested overwhelmingly, I think, in how to present data and multi-sensory presentations of data, not just visual presentations. I'm also interested in the way that the brain processes multi-sensory information normally. And so this finding in synesthesia was, to me, very interesting. It has implications for those of you who are interested in consciousness, also for the basis of consciousness, but I think that's a difficult topic for me to discuss this morning, so I may leave that one for my next visit. The other interesting observation that we made that I want to talk to you about this morning was in the case of lip reading, because again, this is transsensory processing. Lip reading is a very interesting thing. If you're in a bar or a noisy party and you can barely hear what people are saying and you have difficulty understanding them, you will use their lip movements to help you to understand. You will watch their lips, and by the movement of their lips, you will correlate that with the sound you're hearing, and that will give you a large improvement in how you can understand people. Interestingly enough, it doesn't work across languages. It's useless to me in understanding Portuguese. This is another study. But it works very well for me in English, and it works very well for you in Portuguese. And the interesting thing about lip reading, and we published this in Science in I think 1997, is that if you show people a picture of moving lips, they respond in the area of the brain that processes moving lips, which is this area over here called V5, the motion perception area of the brain. But they also respond in the temporal cortex, this area at the side of the brain, which is indicated by the other arrow, which is the area that normally is involved in processing voices. So these people, when they see a picture with no voice, no sound, will have the sensation of hearing the sound associated with that picture. And this is quite an interesting phenomenon. I think these transsensory phenomena, how one sense impacts on another, I think are extraordinarily interesting things to study, and they have a big part, I think, in the way we communicate information. I mean, we know a lot of examples, for example, where mismatches between senses produce terrible problems for us. If we see food advertised on the TV, some colors we like, some colors we don't. Mostly, with the exception of vegetables, the color green is not an appetizing color. Normally, if you see green food, you really don't want to eat it. In most cases. If you saw green meat, for example, you certainly wouldn't want to eat it. So this interaction between the visual appearance of an object and its taste value or its value in another sensory modality is very interesting. And in fact, I'm continuing to work with a group at the University of Oxford in this area, right to this day. Now, transdisciplinarity. This is really the major reason why I'm here. Now, I think it's pretty clear to you that I'm probably quite a strange person in terms of hopping between disciplines anyway. I started life as a biochemist. I then became an image analyst. I became interested in transsensory phenomena. And this actually, the story got worse or better, depending on whether you think this is a good idea or not. Better, I think, in the context of today, because I'm talking about this cátedra and I believe in transdisciplinarity. But essentially, one of the questions that we came across in 1997, there was a very interesting meeting took place in 1997. I went to a cocktail party. I went to a drinks party. And while I was there, I met a guy from the oil industry. And this guy said, what do you do? And I said, I process brain images. And immediately he went and got himself another drink and said, oh, that's very interesting. But strangely enough, he came back and he said, well, I work in the oil industry. And one of our problems in the oil industry is we make seismic surveys. We use sound to work out what's going on under the surface of the Earth. And we often make seismic surveys several years apart, but we have no way of relating those surveys exactly to each other, so we can see what's the difference that has occurred at a particular point. And immediately I said to him, well, this is an image registration problem. This is an image realignment problem. All the time in brain imaging, we have a problem with people moving their brains. Maybe, just maybe, some of the mathematical ideas that we use in functional imaging may be useful to you in being able to study these two seismic surveys. And we submitted an application to a scheme in Britain called LINK, which is an idea to try to get industry to work with academia. And I think this was the most effective grant application I ever wrote. I think I wrote it in 3 hours, and I managed to get £500,000, 2.5 million reais from the British government for this project. So I think that was a fairly successful 3 hours work. I should say I've never repeated that since in my entire scientific career. And we actually obtained some very interesting results from that. Again, these are very complex data sets, but the right-hand picture is a picture, what this is actually is a picture of the rate at which sound is transmitted through the surface of the Earth. And this is fairly, if you're a geophysicist, you'd probably know exactly what this meant. And this is a picture of the bed of the sea, the ocean bed under the North Sea, which is one of the oceans close to Britain, close to the United Kingdom. And this area, the pointer's not working very well, but I think you can just about see this area over here. This black line is in fact the area that the particular oil company who own this bit of the seabed were exploiting to remove oil. And they were interested in trying to work out whether this area had changed over the 5 years that they've been getting oil out. In other words, what change had occurred exactly at this point. And we managed to take 2 of their surveys and line them up with each other. And the picture on the left is just simply an indication of where the biggest changes have occurred. Now, I don't expect any of you in this room could interpret this picture. I'm pretty sure that I can't because I'm not a geophysicist. But the geophysicists were very happy because this told them exactly what they wanted to know about how much oil had been removed and how much more they could remove. So this was my first attempt at transdisciplinarity. Can you use methods developed in biochemistry to study problems in geophysics? And the answer, I think, is yes. Now, so basically, it's frequently the case in science that we have very similar problems across disciplines. The normal situation is that we don't know. I mean, if you think about the last story that I told, the only reason that I got involved in this study was because I met a man from the oil industry in a cocktail party. I mean, I don't know what kinds of social lives you have, but I don't normally sort of talk to lots of people from the oil industry. I don't walk along the street in London and meet lots of people who work for Esso and Statoil and Exxon. So this was unusual. This was an unusual event. And I think one of the things I'm interested in the Cátedra is how do we make this event easier? How do we catalyze this kind of event? How do we make the situation so that we don't have to rely on these chance meetings in order to do what turns out to be very interesting scientific work? It's interesting that wavelet, the fractal technology that I've been using in functional imaging, it also turns out to be very useful in other applications in geophysics as well. Okay, now I'm going to talk about my collaborations with Brazil a little bit now. This is, I think, probably the part of transdisciplinarity that you're most interested in, because this is what brought me here in the first place. As Marco said, we actually began working with Brazilian scientists in 1988. And Marco and I did a lot of work together with Andre Massancini, various other people, Angelo, who's in the audience as well, I think, Angelo Ribeiro, did a lot of work in London together over a period of about 10 years. And in 1998, Marco and I tried to say, well, can we make this a more formal arrangement rather than me just popping over every 6 months and as doing good work and publishing a paper? Can we make this slightly more bureaucratically solid? And we actually applied for a grant about a year after that from the Wellcome Trust, which Marco has mentioned. And this was our first formal collaborative link between London and Brazil. And interestingly enough, this got nothing whatsoever to do with brain imaging. What this was all about was Marco does a lot of work using confocal microscopy. And any of you who've heard Andre particularly talk, I mean, I've heard Andre give a number of presentations about confocal microscopy, and he's one of the best lecturers I've ever heard. So Andre, well done. Andre explains this thing very well. And it's basically a technique for imaging very thin sections of cells. And what Marco's group are doing with Marcos Vinicius Gomez is also in the audience, is to use this technique to look at properties of ion channels and to look at proteins moving between membranes within cells. And it turned out again that Marco and I, when we applied to the Wellcome Trust, put forward the idea that maybe some of the methods that we've been using in brain imaging might be useful in confocal microscopy. Again, we were mainly interested in this question of movement. When you're actually studying cells in the confocal microscope for 5 or 10 minutes, these are living cells and they move while they're in the microscope. The question was, could we use methods developed to look at movement in neuroimaging? Could we use those techniques in confocal microscopy? And this was the reason for the Wellcome Grant. And this is basically some results, and my apologies to Andre, because these are not the best results we've got, but they're the only ones I had when I made this lecture. Basically, the top row is before motion correction, and the bottom row is after motion correction. And what we were doing here was looking at something called correlational analysis. We were looking to see which parts of cells are actually doing the same thing at the same time. And the brighter the color, the stronger the correlation. That's the only thing you need to know for this lecture. What this slide shows very clearly is that motion correction hugely improves our ability to detect correlations between areas in cells. So this is another example where a technique which was basically not, in fact, I think isn't used at all in confocal microscopy. I think we've just published this in the journal Cell Calcium. And it'd be interesting to see how much people take this on board. Now, bidirectional transdisciplinarity. This is an interesting idea. This is looking at it from my angle. Are the techniques that I'm using in Brazil going to be useful back in London? In other words, is there an export in both directions? a movement in both directions? And the answer is yes. I'm now using techniques that I developed while working with Marco on confocal microscopy back in my researches in London. Now, this is the part of the talk where I'm taking the greatest risk, because this is the part of the talk about which I know least, but in which I'm most interested in making progress. And this is, can we actually make a quantum leap? And can we say, forget about just staying within sciences, can we move outside of sciences and look at transdisciplinarity? Can we look at, for example, image processing in the fine arts? What can we do? What are the questions? On the surface, there looks to be a fundamental difference between science and arts. Science, as most of us practice it, is essentially an analytic process. We're interested in finding out how things work. Art, in general, and there are people in London who disagree sometimes when they go to Tate Modern, but art is generally a creative process. And I think, I don't actually believe there is a fundamental difference, or such a fundamental difference between the mentality in art and the mentality in science. I think that creativity is important in both areas. And again, one of my interests in the Cátedra is to see if we can just foster the idea of creativity in working with images. By working with images, I don't mean fractal analysis to publish a paper in a scientific journal. I mean, are there interesting things we can do with images in terms of visual presentation, visual representation, the creation of images, the manipulation of images? Now, there are some areas in which basic scientific type image analysis techniques have been applied in the arts for a very long time, and I'm sure you're all familiar with X-ray analysis of images, which is used very frequently to see something about the history of a picture or to look at its authenticity. This is very commonly used, and I'm sure you're all familiar with that. But there are more significant and more interesting ways of using image analysis, and I think as computer power has improved, these techniques have become more common. And while I was thinking about this Cátedra in London, I actually again made a chance meeting with someone in an art gallery in London. Chance meetings are clearly a very important part in the career of a scientist. I had a chance meeting in an art gallery where the guy that I met told me about something called the Artiste Project, which is interesting. This is a collaboration between art galleries and museums in Britain, Italy and France, with the aim of using sophisticated image analysis techniques for a variety of reasons, for the restoration of paintings, for the analysis of authenticity of paintings, but also as a cross-referencing system for access to paintings. This is sort of idea that I think is going to come up in the next edition of Windows, the so-called Longhorn edition of Windows, is cross-referencing data by image properties, picking out common features in images that can be used in a database. So organizing data in a way that's easy for you to use rather than having to organize it in a way that appealed to some computer scientist back in 1995 or 1985. Now, there are really too many possible applications of image processing in arts for me to talk about conveniently, but I'm going to show you a couple of interesting applications that I've seen. The University of Oxford in London, the robotics department, are doing some work on attempting to see whether you can extract three-dimensional features from two-dimensional images. In fact, there are a number of groups working on this. There's a group also in Washington in collaboration with Microsoft and New York University doing much the same thing. And I've actually been looking at the software that they use because I have some interest in doing this kind of thing myself for scientific reasons as well as creative reasons. And I'm just going to show you a couple of results from the robotics group at the University of Oxford to show you what can be done. This is a very famous painting by Vermeer showing a girl playing a piano. And this is what the University of Oxford have actually done to that picture. This is a 2D image. And they've actually done perspective transformation on that image to allow you to literally get inside the picture. I think this is quite interesting. This is not, it's interesting from a creative standpoint. It's interesting from an image manipulation standpoint because there are things we can do using this technology. It's frequently the case that I want to represent a 2D surface as a 3D object, and this software is actually very good for doing that. And here's another example, another very famous painting, an even more spectacular perspective transformation. This actually places with the possibility of literally getting inside paintings. I mean, this places with enormous possibilities for fraud, apart from anything else, because we could put people inside paintings who weren't there originally. And not only can we do that, we can put them in the right place So the perspective looks absolutely perfect. And there's going to be, in a minute, there'll be a view of the ceiling of this. And this is all obtained from a 2D image. So as a plaything, this is interesting. And anybody who's interested, I've got the website if you want to see more of these images. But it's an interesting scientific tool as well as a plaything. And I think one of the projects that's well worth looking at in terms of thinking about what we could do here is the Grail project, which is a project run, again, by Washington, New York University, and Microsoft. And they have huge numbers of interests in animation of, for example, representing bird flight, representing human movement, 2D to 3D transformations. I mean, basically, it's worthwhile. I've got the website at the bottom there. It's really just worthwhile visiting this website and seeing what these people do. And I have had enormous fun playing with some of the software that I've got out of this site and looking at the various things that I can do with it. So basically, there's a creative aspect to all of this, and there's an image processing aspect which is useful scientifically, and I think this is what transdisciplinarity, I guess, is all about. I'm accustomed to working with 2D, 3D, 4D data, and I said about 20 minutes ago that I have a big problem in representing that data in a form that's accessible to people. And some of the ideas that I've come up, actually while I've been here, some of the thoughts I've had about this have greatly aided me in thinking, how on earth do I represent a brain activation in a form that people are really going to associate with and understand? Before I get on to that, which is the final slide that I'm going to show, this is another interesting image processing application that I want to, from the Grail project, which is context transfer. Okay, the top right-hand image, this one up here, is a genuine picture. It's a digital image taken from the air of a river in the United States. What the people then did is they took that image and they simply hand-colored it to bring out certain features they were interested in, for example, trees, the river, the area surrounding the river. They then, and that's the top left picture up here. Sorry, this isn't working very well, but the bottom left picture shows a manual transformation they've done. They just said, okay, let's create a scene where the river's in a different place, the woods are in a different place. And then the program, and I actually ran this thing here on this little laptop that I'm using for the presentation. It took about 6 minutes. It's transferred the context of the original image to the new image. So it's actually produced a really very lifelike picture of a river scene by transferring the context from the top right-hand image into the bottom right-hand image using the information on the left side of the picture. And this is also enormously important in some of the applications in science that I'm interested in, using neighborhood information to help us to sort out details about images. And also, as I say, it's fun. It's great fun doing this, seeing the way that things... One of the things you can do with this program is to take a photograph of yourself and turn it into a painting by Stanley Spencer or Picasso. It's quite interesting. Okay, so my conclusion is that our ability to represent and manipulate digital images seems pretty well limitless. It's limited only by our own imagination. And we can make progress much more rapidly if we learn and assimilate ideas from other disciplines. My aim here is to help, as far as I can possibly do, that interaction process. These interactions have been enormously beneficial to me, and the setup here at IEAT is one that doesn't exist in Britain. I actually have a working environment here that's both enormously beneficial and also pretty well unique in my experience in my area of science. And I've also learned a great deal, even in the 1 month I've spent here, by just swapping ideas with people. Finally, now this is the most interesting slide I've ever presented, because this slide isn't actually here. This slide is on a website in Denmark. And it's basically part of something called the Visible Human Brain Project. And it's a way of representing brain data, three-dimensional brain data, in a form that's accessible to people. So this is the kind of data that I work with. And it's a virtual reality environment. So if I just set this brain spinning, and you can actually see there's a wonderful sort of thing that looks like the people from Mars Attacks. If any of you have ever seen the film Mars Attacks, this guy looks exactly like the people from Mars Attacks. But you can also see the brain there, and what I can do is I can put an activation in the back of the brain, and you can actually now see when the brain comes around. What I can also do is, if I don't like the guy, I can remove the skull as well. And as I said, the interesting thing about this is not on my computer. This is the miracles of modern technology. This is coming from Copenhagen direct as we speak, basically. So this for me is a huge step forward, and it's a creative method of representing neuroimaging data in a form. We can fly inside this brain, we can teach people about relationships in neuroanatomy, we can do all sorts of things that we could never do before. And I've just started to play with these programs here, and in fact, yesterday I managed to get a virtual reality environment out of one of my own brains. It's nothing like as sophisticated as what I just showed. I've just gone to the end of the slide, so I won't go back. But I've actually managed to produce essentially the same environment here that I can manipulate. So I think the story is, when I first came to take up the Cátedra, I believed in the IEAT project in transdisciplinarity. I believe in it a great deal more now even than I did then, because I think that the ability to sit and think, and as we were saying in a meeting we had on Tuesday, the ability to change ideas, to swap ideas with people in other disciplines without the fear that they will say to you, that's really stupid. You shouldn't be saying that. The ability to speak freely, to learn from other people, I think this is what transdisciplinarity is all about. And if I can achieve that during my visits here, I shall be extremely pleased. And I thank you for your attention.
Ok, então a gente gostaria de abrir então a sessão para perguntas. Podem ser feitas em português ou em inglês. Escrita? Escrita ou falada? Alguém quiser ver escritas?
I think probably 30 years ago the answer was yes, but and that's an admission probably I shouldn't make. No, in the scanner, no, because there are ethical reasons really mainly preventing us from doing that. We have got some projects where we look at differences in perception. We've managed to get a few things through our ethical committee to look at cocaine, strangely enough, but not LSD. The problem with LSD is it's perceived as less of a social problem than cocaine, so we can get ethical committee permission to look at cocaine but not LSD. But they're interesting experiments. I published a paper a few years ago, I can't remember the date now, with a guy called Dominic Fitch, I think in Nature Neuroscience, where we looked at people who were just asked to imagine different types of visual images. Just literally lie in the scanner, in the dark, and imagine a rough texture or a smooth texture, or a brick, or a house, or a bird. And we imaged these people. And we actually managed to show that the parts normally involved in processing objects of that type were actually activated by the act of initiating a thought about those objects. So it's interesting. The 2D to 3D transformation. It's 5 groups that I know of doing this, and a lot of the software is freely available. And in fact, I've got the source code for it. In fact, I'm rewriting some of it. Because what I do mostly is programming. It's what I do for a living. What I do with the programming afterwards is another matter. There are packages that are freely available that will allow you to try that out. But I think the Oxford package, the one that I showed the Vermeer picture, is very, very sophisticated. Most of those packages simply give you a 2D picture, and they ask you to decide whether there's a part of the image where you simply don't know what's behind it, so you cut it out. And there are other parts of the image where you can say, well, there's a sharp change in the gradient at this point. So you give the program a lot of information. But the Oxford program, I think, runs unsupervised. It did those transformations without any user input. And it does it by analyzing the perspective in the image. So it works best on Renaissance paintings with fabulous perspective, or later paintings with fabulous perspective. It works best when you can clearly identify the perspective features of the image. But there are other programs that don't need that, that don't produce such utterly spectacular results. You mean what happens during those perspective transformations? I have no idea. This is real transdisciplinarity, isn't it? When I do brain imaging on what happens on a perspective transform that actually I have engineered using another, yeah, okay. I don't think I'm not aware of anyone doing that. There's no reason why it can't be done. You could show those pictures and see what happens, but I'm not aware of anybody doing it. Actually, on another point, which is not part of a question, but on Tuesday, I think we had a presentation about production of sound from images. And this is extremely interesting to me because, again, this gets into this cross-disciplinary, this cross-sensory interest that I have. I mean, if you like, it's exactly what it's doing in the opposite direction what synesthetes are doing naturally, if you like. It's associating a sound with an image rather than an image with the sound. It's a bit like the lip reading phenomenon. There are lots of things to do. The only problem is I only have one life, and I'm limited in the number of computer programs that one can manipulate. But it's interesting. I mean, I think we are literally only limited by our imaginations.
Mais alguma pergunta?
Sim. 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 Acho que é possível. Na verdade, não é uma área que eu conheço muito bem, mas acho que é possível. Acho que tem grupos de pesquisadores no mundo trabalhando nesta área. Na verdade, não conheço os resultados. Não posso comentar.
Verão?
Fala alto. Sim. Você pode. Ok. Ótimo.
I'd like you to compare the situation of transdisciplinarity as you see here and in Britain, if you see anything similar.
I think this is probably the best question you could possibly ask me. I actually said the other day, and I was not being flattering or disingenuous about this, that the situation that I have here is unique in my experience. There are probably places in Britain where the transdisciplinary environment exists in a similar form, but I am not aware of them. There are certainly places in the USA where this environment exists, where you've got what you might call think tanks, where you just assemble a group of extremely intelligent people from a number of disciplines and ask them to come up with good ideas, and really just don't place limits on what they do. But I don't normally operate in one of those environments. I operate, I think, probably like you do and like most people do, in a restricted academic environment where we're just interested in publishing papers in our own area and getting grants and all the things that we have to do to justify our existence as scientists. This is unique for me, but I think maybe it's a luxury of being a professor titular là in Londres catedrático aqui também. Because now I don't have to justify my existence so much as when I was a postdoctoral student. Now I can do things that I actually enjoy. And maybe you need to be 55 years old and have 2 professorships to do that. I don't know. But it's, the environment here is extremely good, and I'm really not saying that to be flattering. It happens to be the truth.
Well, you said you didn't want only to deal with imaging in ill brains and people with some psychiatric illness.
Yeah.
You want also to image normal brains and another brains. Have you already seen something or about experiments made with people in states of meditative states?
This is a fabulous question, because in fact this work is just beginning. There are 2 areas of study that I'm literally just starting. One is in London. One is to look at people in meditative states. The other is to look at people under hypnosis. The meditative study has only just started. The hypnosis study, we've actually got some results showing that if you hypnotize someone and tell them that one of their limbs is paralyzed, and then ask them to try and move that limb, the area of the brain activated during movement totally fails to be activated. In other words, this suggestion effectively produces in the brain a situation of real paralysis. And I think that's very interesting. I think the insights we can get into brain functioning by using fMRI again, there are some limitations on the kinds of experiments we can do, but within those limitations we can ask some very interesting questions. But actually, strangely enough, I didn't come here mainly to talk about fMRI. I had to talk to some extent about it because it's what I do for a living, but it isn't my main interest here, although I think the establishment of an imaging centre here, which I know Marco and I are involved in, would be obviously a huge step forward. Because we've got an enormous amount of expertise that we could bring to that. But I'm actually interested here in moving outside of functional imaging, if you like.
As pessoas podem levantar a mão antes, que vai me facilitar a vida.
There's a paradigm in using functional MRI, which is parts of the brain are associated with function, localizationism. Suppose that paradigm is not true. Suppose there is a time issue of the same brain area being activated, and it's just neurons being or firing at different rates or different timings or different timetables. So in that case, you would have differences in perception, although the same area of the brain would be activated.
Yeah, you ask a very good question here. fMRI isn't very good at getting at timing on what you might call a neurophysiological scale. It's very good at looking at timing on the scale of seconds. What the smart money is on, what people are doing, is if you want to do neurophysiology, real-time neurophysiology, and you want to localize where that's happening, you will do fMRI, but you will also do EEG. In fact, exactly what Michel is doing with both of us in London. His project is, in fact, to do exactly that kind of combination.
Eu estou preocupado assim, em saber, além das bases da física ou da arte, no campo da educação, da antropologia, se você considera esses autores aí, tipo Edgar Morin, né, e como é que ele tem contribuído nessas conexões que você faz?
Nas outras áreas, acho que eu tenho problema só, problema de tempo, problema de ter uma limitação nas horas da semana. E por isso eu acho que eu preciso limitar um pouquinho as colaborações aqui no Brasil. Isso é um problema. Eu gostaria muito de fazer pesquisas que praticamente todas as pessoas que estão interessadas nas imagens, utilizar as imagens nas pesquisas. Eu tenho um problema simplesmente de habilidade de participar, de compartilhar o meu tempo.